In the last lecture, we said that we would talk about residual plots in this lecture, and at the beginning of this lecture, we said that we would talk about residual plots later. Let's actually talk about residuals and residual plots now. A residual plot can tell us quite a bit about the quality of our model. Now, there are two different ways that we can make residual plots. In the simple linear regression case, where we just have a single feature, we typically can visualize our residuals on the y-axis and our x value on the x-axis. In the multiple linear regression case, that doesn't make as much sense, and so what we do is we plot residuals on the y-axis and our fitted values y hat on the x-axis. Now, we will momentarily look at some residual plots, but what should we look for? Well, a good residual plot has no pattern. What this means is that our model represents the data, the relationship in the data, I should say, quite well. If you see some sort of clear pattern in your residual plot, then that indicates that there's some underlying structure between the variables that you're looking at that your model hasn't yet captured. And so in such a case, you may want to transform one of your variables, or more typically, add more features so that you're explaining more of the sort of relationship between your features and your y values. Another property of good residual plots is that the vertical spread is roughly the same throughout the entirety of the plot. And again, we will look at an example of this momentarily. But if this is not the case, then the accuracy of our regression model is questionable. And we will take a look at why this is sort of one of the assumptions of the regression model when we talk about the bias variance trade-off. Now, I'm not saying that the residuals should be exactly the same across our plot, nor am I saying that our residuals even need to be small. All I am saying is that the size of our residuals shouldn't change dramatically as we, alter our position on the x-axis. So for instance, it shouldn't be the case that really big x values have really big residuals and really small x values have really small residuals. The size of the residuals should roughly be the same if our residual plot is good. For this section, I will work out of the notebook. I know students really like when we do sort of code demos, and I haven't really done one in this lecture. With that said, there is a little bit of extra stuff in this lecture notebook that I didn't cover explicitly in the videos, but you should go and take a look at it if you're interested. But for now, we will work from the residual plots section. So the examples I want to look at are from the Anscombe's quartet dataset that we've looked at sort of in the last lecture. So, Anscombe's quartet has 4 datasets, but I will just look at dataset 1 and dataset 2. And by the way, you can actually load these yourself by calling Seaborn's sns.load dataset. This is the first dataset, and this is the second one. It seems like there's a linear trend between x and y in the first dataset, but it doesn't really seem to be the case that there's one in the second relationship. And the second one seems like there's some sort of quadratic or parabolic relationship between x and y. Let's fit simple linear regression models to both datasets and look at the residual plot. So here I'm using scikit-learn's linear regression package. The usage of scikit-learn's linear regression will be, talked about extensively in the following lecture, but for now, just, think about this as fitting our model, determining what y hat is, and determining what our predictions are. And so now I have my true x's, which is just the x column from the Anscombe's dataset. I have my true y's, I have my predicted y's, and I have my residuals. Since we're looking at the simple linear regression case, I will take a look at residuals on the y-axis and my x values on the x-axis. And doing that yields something like this. And so we can see that there's no clear pattern in this residual plot. It's also the case that the sort of spread of our residuals vertically seems to be relatively the same across, our x-axis. It's not the case, for example, that small x values all have small residuals and big x values all have big residuals. It seems to be the case that there are both small and large residuals, at least in terms of, their absolute size, all throughout the x-axis. So there's no pattern in the residuals, and the vertical spread is, roughly the same throughout. So we would say that this is a good residual plot, meaning that our linear model that we determined fits these values quite well. Let's do the same for the second data set. And as we saw here, that the relationship isn't exactly linear, so we shouldn't expect to see a good residual plot. And so the residual plot here looks something like this. And so this is interesting. Firstly, there's a clear pattern in the residuals, right? Whereas over here, there's no real discernible pattern between x and our residual values. Here, the relationship between x and our residuals is clearly quadratic or parabolic. We could almost exactly fit a parabola through these values. And so what that's indicating to us is that we likely need to add more features in order for our model to be, any good. Now, I didn't mention this earlier, but this black line represents when our residual is equal to 0. So if a point is, on or near this black line, it means that for, this x value, we made a very accurate prediction, and the further away it is from this black line, it means our prediction was not so accurate. Here, the further we got from x is equal to 9, which is where these points sort of seem to be centered on, the larger the size of our residual was. So it's not the case that vertical spread was roughly even throughout our plot. So this is another reason why a linear model was likely not the best choice for this specific set of values. Now, a property that we are going to discuss momentarily of residuals is that they always sum to 0 as long as our model, that is linear, includes an intercept term. Now, this is true even if our model is a poor fit to our data. So let's take a look at the sums of the residuals for both of our models. Here, you can see that they're, something times 10 to the minus 14, which for all intents and purposes is 0. The only reason they don't appear as exactly 0 is due to numerical precision issues that come as a result of how computers store numbers. So the residuals sum to 0 when we have an intercept term, even if our model is no good. And what that means sort of visually is that the negative residuals balance out the positive residuals. But as we can see here, that doesn't mean our model is any good. Let's take a look at a residual plot in the multiple linear regression case. For this, let's go back to our tried and true NBA dataset. So let's use assists and 3-point attempts to predict points, as we did in the last lecture. So I'm doing that here, and you can notice that the code for this is not really any different than it is for the simple linear regression case, which is one of sort of nice properties of scikit-learn. I will use Plotly to make the visualization here, just so it's a little more interactive. And so you can see here, since I have multiple features, I didn't pick just one to put on the x-axis. Instead, I put my predicted y value on the x-axis, and the residual remained on the y-axis. Once again, this black horizontal line represents the line where the residuals are equal to 0. You can see here that once again, there's no clear pattern in the residual plot, but it seems like vertical spread varies a lot with our position on the x-axis. When our fitted values are relatively small, like less than 15, most of the residuals are very closely clustered around 0. But as we increase the size of our fitted value, so like with the fitted values 20 or 25 or 30, the residuals seem to vary a lot more. And so this is what I was referring to earlier by uneven spread of residuals. The residuals sort of over here are not as closely clustered to the x is equal to 0 line as the residuals over here. Lastly, we can take a look at the sum of these residuals, and we will once again see that since our model includes an intercept term, the sum is equal to 0. If our model doesn't include an intercept term, it's not clear what the sum of the residuals will be. And so now let's talk about some of those properties. And in the slides, we have the same residual plots that we just looked at in the notebook. Let's look at residuals from the perspective of the geometric derivation that we just walked through. So when we were determining our optimal model parameter theta hat, we stated that it satisfied the property that the residual vector was orthogonal to the span of x. And the way we denoted that was by saying the product of x's transpose and the residual vector was 0. One property that follows from there is that since the predicted response vector y hat, which is again just x times theta hat, is in the span of x, it's also orthogonal to the residuals. And so the dot product of y hat and e is 0. Again, x over here is a matrix, y hat is a vector. This is true no matter what the features of our model are. But when our model includes an intercept term, things become slightly more interesting. when our model includes an intercept term, we have a column that contains all ones in our design matrix. And some interesting properties follow from that. One property that's true is that if you take, the dot product of this column of all ones with the residual vector, you get 0. Now, proving some of these properties that we are about to look at right now is an exercise in one of the homeworks that you will work on in this class. So I'm not going to explicitly spell it out for you here, but all of the key ideas are sort of presented to you right now, and you sort of need to put them together yourself. So when our linear model has an intercept term, the sum of our residuals is 0, and the mean of our residuals is 0. And so this is why the sort of positive and negative residuals cancel out regardless of the quality of our model as long as there's an intercept term. And so if you were to sort of add up the negative distances from this horizontal line and the positive different distances to this horizontal line, the result would be 0. And that's true of all of the residual plots that we looked at, since all of these models had an intercept term. If there's no intercept term, the sum of the residuals may or may not be 0. And that's something we will also look at in a future lecture. Another property that holds because of this first property is that the average true y value is equal to the average predicted y value. Again, this is a proof that you are going to walk through in the homework, but they sort of all stem from the fact that our residuals are orthogonal to the span of x. So that's it for residuals.